All right, let me do two more examples of product rule, and then we'll talk about the sum rule. So how many numbers between 0 and 999? We know there's 1,000, right? So, so if we think of the number 7 as being like 007, and we think of the number 15 as being 015, and right, we can just say how many 3-digit numbers are there if we include leading zeros as being legal. So how many ways can we create a 3-digit number? Well, there's 3 subtasks. Pick the first digit, pick the second digit, pick the third digit. How many ways can we pick the first digit? 10. How many ways to pick the second? 10. How many ways to pick the third? 10. Multiply those out. There's 1,000 possibilities. That's why there's 1,000 3-digit numbers, if you count 0 as a digit. Okay, let me show you one other example. Let S be a set with 5 elements. And I'm just going to call them S1, S2, S3, S4, S5. So again, we're putting an ordering on these elements even though sets are not ordered. But I want to be able to refer to the elements individually. So how many subsets of S are there? So suppose T is a subset of S. We know that to be a subset, it has to be comprised only of elements from S. Agreed? So the only possible elements in T are S1 through S5. But it's a subset. It does not have to contain each or any of those elements. So I'm going to specify 5 subtasks. T1, decide whether S1 is in my subset. Task T2, decide whether S2 is in my subset. Task T5, decide whether S5 is in the subset. Choosing a subset is now a succession of 5 tasks, which is choosing whether each of these elements is going to be in my subset. If I answer that question for each of these elements, I've defined a subset. And any subset can be gotten by suitably answering these 5 questions. So how many ways can I answer this question? Is S1 going to be in my subset? 2 ways. Either it's in the subset or it's not in the subset. So N1 is 2, N2 is also 2, N5 is also 2. So the total number of ways I can do this succession of tasks is 2 multiplied by itself 5 times, which is 2 to the 5th. So there are 2 to the 5th possible subsets, which is just revisiting the idea that if we take the power set of S, that's the collection of all possible subsets, the cardinality of that number of things in there is going to be 2 to the 5th. And you can generalize this pretty easily to show that for a finite set S, the cardinality of the power set is 2 raised to the cardinality of the set itself. Now if S has 5 elements, I can do this, and I can very formally show that the power set has 2 to the 5th. And if S had 6 elements, I could do this and very formally show that it has 2 to the 6th. But for a set with n elements, how would I formally show that the power set has 2 to the n elements in it? I know you want to say it, because we haven't said it in a few weeks. How would I formally generalize this to all possible n? Someone say it. Mathematical induction, right? Anytime that you can show something for a particular case and you yourself know how to go from one case to the next, mathematical induction lets you say, therefore I can do it for all possible cases. That's the whole idea of induction. And if I know that a subset of 5 elements has 2 to the 5th, if I add one more element, right, I've now got 2 subtasks. 1, choose a subset of this, and then 2, see whether or not that extra element belongs to the subset or not. Number of ways to do this is 2 to the 5th. Number of ways to do that last element is 2. Multiply it out, that's 2 to the 6th. So we can put all this stuff together and get like awesome combinations. All right, so let's talk about the sum rule. So if a task T can be done either by doing T1 or by doing T2, not both, and T1 can be done n1 ways, and T2 can be done n2 ways, then T can be done n1 plus n2 ways. So if you can do T as a succession of tasks, multiply the number of ways to do each subtask. If you can do T by accomplishing either task T1 or T2, add together the number of ways to do those subtasks. So that's the sum rule. Okay, so for example, ordering lunch. Choose one of 5 soups or one of 7 salads. That's all you get for lunch is a soup or a salad, no beverage or anything. So you're going to choose either a soup or a salad. So our task T is to order lunch, and we can do it as one of 2 subtasks, either T1, choose a soup, or task T2, choose a salad. So how many ways can we choose soup if we've got 5 possible soups? 5. And if we have 7 possible salads, the number of ways we can choose a salad is 7. And so the total number of ways we can order lunch is 5 plus 7, which is 12. That's all there is to the sum rule. Now if your task was to order a soup and a salad, right, then you can accomplish your task of ordering lunch by performing T1 followed by performing T2. That tells you there's 5 times 7, 35 possible lunches. But if you got to choose, then there's only 12. Okay, suppose we want to order a lunch plus a beverage. Does anybody use the word beverage outside of like commercials and restaurants? Do you? Okay, cool. We'll keep going with it then. So we want to order lunch and a beverage, right? And let's say that there's 10 possible beverages, because we're at like Burgerville with their soda machine, right? Which I know how to hack, by the way. Oh. I snuck onto the back of an employee tour when they got their new machines. There's 3 bubbles. If you press them in the right order, it brings up like the maintenance menu. It's pretty cool. Yeah. So
there's only 8 possible combinations, right?
Of
button presses.
No, you got bubbles. So go to the. I shouldn't record it. I'll tell you off camera. So you want to order lunch including a beverage, right? So you have to choose a soup or a salad, and you have to choose a beverage. So we have task T, which is ordering lunch, and then we have task R, which is choosing a beverage. And this is a succession. So the complete process is choosing a soup or a salad and then choosing a beverage. So how many ways can we choose a soup or a salad is 12. How many ways can we choose a beverage is 10. So the number of ways we can do both of those is 12 times 10. It's 120 possibilities. So we see combinations of these sometimes where we have a product rule and a sum rule. All right, so there's a conference coming up, and you need to send either a teacher or a student. So you have to pick either a teacher or a student to go to this conference. Bless you. And so we can break this into two subtasks. We can either choose a teacher or we can choose a student. And let's suppose there's 25 teachers and there's 100 students. So the number of ways we can do task T1 is 25. The number of ways we can do task T2 is 100. So the total number of ways we can accomplish task T is 25 plus 100, which is 125. Which isn't surprising if you just think about it without all of the extra layers. You've got 125 people. Your task is to pick one of them to go to a conference. There's 125 ways to do that. And I'm going to make a comment here that if you're here, you're going to benefit from. And if you just watch the video, you'll probably end up losing points unless you listen to this. Don't do this. Okay, no. If I ask you to do these questions, particularly on an exam, don't just draw a squiggle under teacher and say T1 and a squiggle under student and say T2. Take the extra time and say let T be the task blah, let T1 be the task, choose a teacher, let T2 be the task, choose a student, right? These shortcuts are fine if we know what's going on, but when you're presenting something on an exam, you're trying to take this out to a stranger and say, here's my work, proving to you that there's 125 ways to complete task T. So be explicit, right? Somehow do something more than just draw a squiggle and assume that I know N2 is the number of ways to do T2 and so on. But we're being sloppy here. All right, got the sum rule down? Okay, so we got one more, which is subtraction.
Oh, no.
Which is also called the principle of inclusion, exclusion. And we can express this principle in set theory as follows. The number of elements in A1 union A2 is the number of elements in A1 plus the number of elements in A2 minus the number of elements that overlap. Because suppose A1 equals ABC and A2 equals BCD. The union is not going to have 6 elements in it because we've counted some of these elements twice, ABC, BCD. How many elements did we count twice? However many elements are in common between these, in particular B and C. So if we just add the number of elements in these two sets, we've added too much. We need to subtract off the number of things that overlapped. That's the cardinality of the intersection. So this is a factoid that we can rely on, but it really captures the whole idea of this principle of inclusion-exclusion. So let's do an example. So 65 students take CSE 222, and 30 students take CSE 215, and 25 students take both. And I consider someone to be a CS student if they're taking either one of those courses. So how many CS students are there total?
95.
Probably smaller than 95.
7.
Oh, right. Yeah, just 7.
Right, because most of the students that are in here are also in 222. But there's a few in here that aren't. So 70 is a good answer, right? How did you get 70?
Well, we know that 65 are in CSE 222 and 30 are in 215. But if you look at the students that are in both, that leaves 5 that are even just one or just the other.
Mm-hmm.
And since the CS major just has to take one of the classes, we take the difference between the lowest value with the set that both are in, and we add that to the largest value.
Okay, I think that works.
You could even take
And that's really just this. So logically, right, there's 25 students taking both. There's 30 students in here. There's 65 in there. There's a total of 95 people, right? But we know that some of them are duplicated. How many of them are duplicated? 25. So we can break this into some sets. So A1 equal a set of CSE 222 students. Let A2 equal a set of CSE 215 students. Total number of students will be the number of elements in A1 union A2. And our principle of inclusion-exclusion says that's the number of elements in A1 plus the number in A2 minus the number in the overlap. Well, the number of students in set A1 is 65, the number in A2 is 30, and the number of students that overlap is 25. So 95 minus 25, there's your 70. So you add some and you take some away, inclusion, exclusion. And there's all kinds of good questions in the book about this, where you have people going to movies, and some of them go to both movies, and some go to one, and so on. All right, so let's do one computer science-y example. So, question. How many 8-bit numbers start with a 1 or end with 2 zeros? So we're looking for the numbers that either have the form this or the form this. So how many numbers are there in this first form?
7 to the 8 over 2.
7 to the 8 over 2.
Yeah.
How'd you get that?
Because the truth table, so if you do a truth table of just 2 bits,
Mm-hmm.
2 combinations of 1 leading and 2 combinations of 0 leading. If you do the same with 4, you have a set number of combinations with 1 as the leading, and then you have it mirrored with an equal number with 0 as the leading. So
Okay.
you take all of the combinations of the bits, which is 2 to the bit place, right?
Right.
And then you divide it by 2 because half of those are going to start with 0.
It's got a good point.
But how did you get 7 to the 8th over 2?
2 to the 8 over 2.
Oh, 2 to the 8th over 2. Okay, good, good. All right. Okay, so yeah, so that's perfectly right. So from the picture, one way to see that is we have 7 bits that we need to fill in. Right, so if you know the number of 7-bit numbers is 2 to the 7th, that gets you the answer, 128. Or you can break this into 7 successive tasks, choose each of those bits. 2 ways to do each, that's 2 to the 7th. Or you can start with 8 bits, 2 to the 8th, and since this first bit is fixed, divide that by 2, because half of them are going to start with 0, half will start with 1. So the total number of ways to do this is 2 to the 7th, which is 128. Cool. All right, how many ways can we find a number in this form, something 8 bits ending with 0, 0? Similar idea.
2 to the 6th.
2 to the 6th. We've got 6 bits here we need to fill in. So there's 64 ways to how to write a number in this form. Okay, how many numbers are simultaneously in both of these forms?
2 to the 5.
Why?
Because you put the 1 there, and then there's 5 blank spots.
All right, so if a number is in both of these forms, it looks like this. And there's 5 bits. And so there's 32 possibilities there, 2 to the 5th. So here's our set A. Here's our set B. So A is all the numbers in this form, B is all the numbers in this form, and we want to know what's the cardinality of the union of that. In other words, how many numbers are in this form or this form. And principle of inclusion, exclusion says it's the number of things in A plus the number of things in B minus the number of things in the overlap. So 128 plus 64 minus 32, so that's 160. Make sense? All right, let me give you the statement of the Pigeonhole Principle, which is where we're going to start on Wednesday. Well, I won't give you the formal statement. Let me give you the idea of the Pigeonhole Principle. Do you know what a pigeonhole is? Do you know what a pigeon is? Okay, so pigeons have been used for all kinds of things. Pigeons are really smart about certain things. You can train them to fly to certain places, and so people used to use pigeons to convey messages. So you take a message and you attach it to the leg of a pigeon and you send it off to the receiving station, and it's a way to transfer information across town. So pigeonholes are just, have a box and make some cubby holes like this, and they're just little spaces in this box where the pigeon hangs out, right? Okay, so here I've got 16 holes. If I have 16 pigeons, each pigeon can have its own place to hang out. Agreed? If I have 17 pigeons, is there any way that I can give each pigeon its own hole? Right? I can't. They're going to have to share. They might all 17 decide to go in one spot. That's fine. What the Pigeonhole Principle says is if I have 16 buckets and I have 17 things, and I put each thing in a bucket, somewhere I have at least one bucket with at least 2 things in it. Okay, that's the whole Pigeonhole Principle. So if you have 17 things and only 16 places to put them, you're going to have to at least double up somewhere. All right, so we'll start with that on Wednesday, and that's going to get us into some interesting and potentially unexpected results. All right, so I'll see you then.